Next up is Mrinal, who's going to tell us about improved depth reductions.
This is joint work with Rafael and Ramprasad. So I'm going to talk about syntactically multilinear circuits, which I realize nobody has spoken about so far. So I'll start by defining them. So these are arithmetic circuits with the following property.
Well, now can you use black or blue?
Okay, so let me start by defining syntactically multilinear circuits. So these are arithmetic circuits where the product gates have the following property. If you look at the sub-circuits rooted on the children, they do not share a common variable. So we'll use this notation throughout the talk. So we'll have, say this is G1, G2. The set of variables that the sub-circuits of the children depend on, they are disjoint. Okay, but at the addition gates, they can share variables, so it's a circuit. It's not really a formula. And these are sort of natural-ish models, and they're fairly well studied. The reason they are natural-ish is because many of the polynomial families of interest for us are actually multilinear. The determinant, the permanent, the iterated matrix multiplication, elementary symmetric polynomials, and so on. And if you try to come up with a circuit for them by yourself, very likely the circuit that you would come up with would actually have this property. Because if you do multiply, if the children do intersect and you do compute non-multilinear things, then there is some cancellation to happen for the final computation. And typically we don't know how to do this. A well-known exception to this is the determinant. For the determinant polynomial, we know poly n-size circuits which are highly non-multilinear. We don't know syntactically multilinear circuits for the determinant, and we probably also don't expect determinant to have such circuits, even though we don't have any lower bounds for it.
Short of some 2n factorial.
Actually, I don't know anything non-trivial for the determinant which is syntactically multilinear. Okay, but they have been studied nevertheless. So it started with this paper of Avi and Noam Nissan from 90s, where they defined something which looked like this and proved some lower bounds for it. But the real important results happened in the decade after that, where so Raz proved formula lower bounds, so super polynomial formula lower bounds for syntactically multilinear formulas. And this was followed up by a bunch of papers of Ran and Amir, where they proved an exponential lower bound for constant depth formulas. Syntactically multilinear circuits. And we will look at what this result is, and this would be important for us.
So constant depth is unbounded fan-in.
Yeah, unbounded fan-in. Yeah.
Add and multiply.
Yeah. And for what it's worth, we know better lower bounds for syntactically multilinear circuits than we know for general circuits. So this was a result of Ran, Amir, and Amir. And then recently with Noga, Elon, and Bentley, we improved it. So we know n to the 2 minus epsilon lower bound for syntactically multilinear circuits. So what we know for them is a little bit better than what we know in general, which is not so much in any case. Okay, so what would be of interest for us would be this particular lower bound. And what Raz and Yehudeyev showed was the following. So they showed that there is an explicit family of polynomials where the degree of Pn is actually theta n, such that any depth 4 formula, depth 4 syntactically multilinear circuit computing Pn has size something like so it's n to the omega square root of n over log n. And the result is more general. It holds for formulas of arbitrary bounded depth, and the bound decays appropriately. Maybe we'll come to it later. And when we started working on this, what we wanted to do was to improve this bound, prove better bounds, better lower bounds for this. And if you have seen these kind of theorems for lower bounds for depth 4 circuits, at some points lower bounds for depth 4 circuits do start implying general circuit lower bounds. So in particular, if you prove strong enough lower bounds for depth 4 syntactically multilinear circuits, it would imply lower bounds for unbounded depth syntactically multilinear circuits. But it seemed that this number, this bound in the current state was a little bit far from where lower bounds imply general circuit lower bounds. So the depth reduction results say the following. So n to the little omega square root d lower bounds for some product circuits imply general circuit lower bounds.
For that D polynomials. For the degree D polynomial.
Right. Yeah. For a degree D polynomial. Okay, so even though these results are proved for general homogeneous circuits, if you follow through the proof, these results actually hold for syntactically multilinear circuits and so on. So in particular, for a degree n polynomial, if we had lower bounds which were better than n to the root n, then we would have general circuit lower bounds.
General circuit lower bounds of the same.
Yeah, right, so of the same kind, so syntactically multilinear circuits.
No, and also n to the root b.
No, super poly.
Oh, yeah.
Okay, so for a while, the plan for us was to at least get rid of the log n factors in these lower bounds, and maybe nothing spectacular happens. And we couldn't do that. And the main theorem here is that this result can be tightened for syntactically multilinear circuits. Theorem is the following. So P is a polynomial. So P is a polynomial computed by a syntactically multilinear circuit of size S. This implies that P can be computed by a syntactically multilinear depth 4 circuit of size S to the order of square root of n over log n. So you should think of S as poly n. So this is n to the root of n over log n.
And it's both the number of variables and the
Right. So here n is the number of variables. So right. So
Degree.
right. So this bound. Good. So what happens as the degree varies? So if degree is much smaller than n over log n, then this is actually a better bound. The usual depth reduction results of Agrawal-Vinay with these new parameters by Sebastian are the better bound. So n to the root d is a smaller number than n to the square root of n over log n. But the moment degree becomes large, then this is a better bound.
So your bound holds even for exponential degrees or only polynomial degrees?
It's a multilinear polynomial, so degree can be at most n. So, but if the degree becomes larger than n over log n, then there's a better bound, and it matches this lower bound. And it turns out, so in this paper, they proved this lower bound for a polynomial which has a unbounded depth syntactically multilinear circuit of size poly n.
Syntactically multilinear means
means-
not because of any cancellations. Is that what it is?
It means this, that every product gate, the children depend on disjoint sets of variables.
Okay.
So in that sense, this is also the right bound. So one can also put a theta here.
Is there a general reduction from generic circuits to syntactically multilinear?
Not that I know of. We don't even know a reduction from a semantically multilinear circuit to a syntactically multilinear circuit. So it's far beyond what we can do. Where semantically multilinear, you impose a semantic restriction that at every gate in the circuit you are computing a multilinear polynomial. This is sort of a syntactic restriction on the structure of the circuit, not the computation that goes. Okay, so that was the result. So I'll say a bit more about this, but questions so far?
This is, I guess, non-constructive in the sense of the previous ones, right? You just show its existence by chopping it somehow, right?
No, all the depth reduction results are actually constructive, pretty much. So you could.
I mean, you get a black box. So the reason I'm asking is, you get a black box reduction for the lower bounds in the PIT setting because they're not constructive, right? So this is what I'm asking.
Okay. So I didn't follow the question, but I think the low bounds are. One could do it by hand. So
I mean,
somebody had.
Given a circuit, you can construct the reduced circuit.
Yeah. And this is true for the general, the usual depth reduction results also.
Well, there is a reason why you cannot apply non-black box heating, non-black box PIT from
Right.
general things.
Right. I'll have to think. I know there's a reason. I'll have to think about it, but we can do this offline.
Offline.
Okay. So, questions so far? So let me tell you a little bit more about what really happens here. So this reduction is also a little bit more general than what's written here. So it doesn't just hold for syntactically multilinear circuit. It also holds for circuits where you're not allowed to take very high powers of variables. So circuits of so-called individual degree at most k. So if you start from a circuit of individual degree at most k, the bound that you get is s to the order of square root of nk over log n.
And syntactically.
This should be syntactic.
Yeah, so this will also satisfy the reduced circuit will have the property that you started. Okay. Also, this depth 4 circuit has a little bit more structure than just the size being this. So the depth 4 circuit that you get is of the form sum over I product over j qij. So I goes from 1 to this bound of s to the order, and so each qij, it actually depends on at most square root of n log n variables. So in particular, its degree is bounded by square root of n log n, but there's more. It just doesn't see too many variables. None of the QIJs actually sees a lot of variables. Okay, questions so far? So let me say something about the proof. So the proof is like a typical depth reduction result in the non-multilinear setting. There will be two steps. So we'll start from a size S syntactically multilinear circuit. And in the first step, we'll construct a what we'll call a balanced syntactically multilinear circuit. I'll tell you what it is, but the size blow up in this step will only be poly S. And in the next step, we go from the balanced circuit to a depth 4 circuit. And now the size blow up will be let me say a bit about what a balanced circuit is. So balanced circuit will have the following property, the circuit that we construct there. So the sum fan-in, you could think of this as unbounded, so it would be some, so the sum fan-in will be unbounded. The product fan-ins will be bounded by a constant, phi, for instance. And every product gate will have the following property. It will have 5 children, and if you look at the degree of the, so let's say this is U, and the children are G1 up to. So if you look at the number of variables in U, the number of variables in any of the children, it's going to be at most half the number of variables in U. So it means that none of the product gates you incur so they're not very skewed. So each of the children is roughly much smaller, roughly half the weight of the parent. Okay, and if you have seen the usual depth reduction results, then there is a notion very similar to this that appears there, where the right notion turns out to be the degree. So this is what happens in, for instance, this work of VSBR. Okay, so in some sense you could think of it as the potential function that we are working with changes from the degree of a polynomial, the degree of a gate, to the number of variables in it. And if you want to work with circuits with bounded individual degree, which was the other statement I mentioned there, then you have to change it appropriately, and then things work out.
So you just scale it pretty much, you just scale it by the constant degree, like the number of variables, just cut down, like double count them up until k or something like that?
Yeah, something like that. So you have to look at the exponent vector, and it's L1 norm or something like that.
So this step might be actually increasing the depth at this stage.
Yeah. So the depth here will be, so since it's unbounded sum fan-in, the depth you can bound it by like order log n, order log s. And so in the first step we go from a general circuit to a balanced circuit, and that incurs a poly blow up, but poly S blow up, but we have this additional structure. In the next step we go from a balanced circuit to a depth 4 circuit, and the gain that you get is actually visible in this step, so I'll show you that. So we have a balanced, and we want to go to a syntactically multilinear depth 4 circuit. The way we do it is the following. So inaccurately in a picture, the way we would depict it would be that we'll make a cut in the circuit. So we'll collect all the gates, collect all gates which depend on at most square root of n log n variables. And then we'll view these gates as sort of input gates. And you view the computation that's happening on top on these gates. So since the circuit is balanced, it turns out that the top computation, the degree of the top is actually small. And also it will satisfy this syntactically multilinear structure. Okay, so now this immediately gives a way of writing a depth 4 circuit. So for the top part, we'll just write it as a sum of monomials. And in the bottom part, we have these gates which depend on a small number of variables. So we'll write all of them again as a sum of monomials. Okay, now the point is that the top has small degree, so the size would be at most, it's a small degree polynomial on at most s variables. So the size would be s to the order of n log n. And the bottom part, you're looking at multilinear polynomials on square root of n log n variables. So the size would be at most 2 to the square root of n log n. And if S is poly-n, they balance out. It's the right number. So it's a bit different from what happens in general, where this big cut here is defined in terms of the degree. So you pick the degree to be something, degree k. The top part will have degree about d over k. So you get a s to the d over k bound here. You get a n to the k bound here because you're looking at polynomials of degree at most k. And then you balance n to the k and n to the d over k. And the right threshold turns out to be k being square root d. Here you're trying to balance s to the n over k and 2 to the k. So the right threshold turns out to be square root of n log n. Questions on this part?
Why was the outer sum s to the root n over log n?
So it's a polynomial of degree square root of n over log n on at most s variables. So you write it as a sum. All right. So this is really where the gain comes from.
Is there any hope to improve by another square root log n? I mean,
This is also tight, like I said, because of Amir and Ran's result.
I'm tied up to showing an exponential or bounds or something.
No, so we know that we can't hope for a general theorem of this form where I can put something little of this quantity here. Okay.
Mrinal. So if you wanted to get polynomial lower bounds for syntactically multilinear circuits,
Yeah, this is basically nothing. So there's some game in the constants which appear here.
yeah, that's what I was wondering. Is it huge?
Yeah, but this constant is not too bad. It's like 10, but it's bad enough.
Yeah.
If you want to prove n to the 10 lower bound, then it seems unlikely that this is the way to go about it. Okay. I have like 5 minutes. So I want to tell you something about how this is proved. So I was hoping that I wouldn't have time left for this, but
All right. Any questions?
okay. So here's the idea is the following. So if you have seen how the usual depth reduction proofs of VSBR work, so Valiant, Skiem, Berkowitz, and Rakov. So this is like that, but with some crucial differences that made it interesting. So the key definitions there is the notion of a quotient of two gates and what's called a frontier decomposition. So it's a bit hard to justify why this is the right definition to look for, but I'll define the quotients. Don't ask me why that's the right definition. So for every two gates in the circuit, so u comma v, we'll define the quotient of u with respect to v. And it's inductively defined. So if u is equal to v, then the quotient is 1. If u is a sum, then the quotient is the sum of the quotient of the two children. Okay, so before I define the next one, we'll follow this. This assumption that at every product gate, the number of variables in the right child is heavier than the number of variables in the left child. So it's a right heavy circuit. Okay, and this is really without loss of generality. It's just a relabeling. So at a product gate, things are asymmetric. So the quotient is asymmetrically defined. And lastly, if V is
That UL times.
UL times, so this is the polynomial computed at UL. Okay, so this is the polynomial computed at a gate. So it's UL times the quotient with respect to the right child. And if V is not in the circuit rooted at U, then the quotient is 0. Okay, so this is a definition. And the reason this comes in handy is the following. So in the balanced circuit that is eventually constructed, you will have gates for all. You will have a gate for all the gates in the original circuit and all the quotients of 2 possible gates. So for all pairs U and V, there's a gate there which computes the quotient of U and V.
So Mrinal, so if the right gate does not have a path to B,
Yeah. Then the
left
quotient.
gate does.
Yeah. Then the quotient is 0.
Quotient is 0.
Yeah. Okay. And the reason this is an interesting definition is because of what happens here. So there's a notion of frontier. So F sub m is the set of all. Okay. So in the case of Valiant et al.'s proof, this is the set of all gates such that if you look at the degree of U, it's larger than, it's at least m, and both the children have degrees strictly smaller than m. So in some sense, when you're going bottom up in the circuit, this is the first time when the degree actually becomes larger than m. In our case, so one of the differences in our proof and the earlier proof was that the frontiers in VSBR's proof were always defined with respect to gates. So degree was the potential function, and the degree could only grow at multiplication gates. So your frontiers will only be multiplication gates. But in our case, we work with number of variables as our potential function. And number of variables can also change at summation gates. And in a homogeneous circuit, degree remains the same at summation gates. So in our case, our frontiers are defined with respect to edges. So an edge is a frontier edge if the number of variables here is larger than m and the number of variables here is strictly smaller than m. And this summation, these edges could have all sorts of gates here. They could be summation, they could be multiplication. So this complicates the structure of how the number of variable evolves over a period of time. And this messes around with what the frontier decomposition really looks like. So I'll just write an equation and stop with it. We'll have 2 kinds of frontiers. We'll have summation gates, edges where the top is a summation gate, and multiplication gates. And so if you take U such that x sub u is larger than m, then you can write the polynomial computed at u . So these are edges in the multiplicative frontiers. These are edges in the frontiers where the top gate is a sum gate. And there are 2 kinds of terms. There are contributions from these guys. There are contributions from these guys. If you look at the usual, the Valiant et al. Proof, this second term is absent there. The first term roughly looks like this. So there's some error term which has to be taken care of in the decompositions. And roughly the way you build a balanced circuit is you inductively build circuits for these guys, and then you write this guy as a sum of product of these things and plug things in, and it works out. Okay, so that's all I'll say. Thanks.
Questions? Yes.
So, I mean, can you combine to get the best of both and avoid this, like, this is better than one and one reading, this is better than the other, and the other better?
I don't know how to do that. But
Okay. Thanks to Mrinal again.